So I can look up here. Closer to it.
The group speaks for the visit and also we can advise. You know which one.
Yeah, right. We need to. Yeah, I think that's fine. From the only thing I want you to do is to tell everyone that the groups for the visit project.
Yeah, but
Yeah, so maybe if you can say it now, yeah. And then yeah.
Can you just have a look? Okay, I think we will then start with hopefully yeah. I mean we said to finish we will run past 6, but I mean I don't know where he will if it's after 6 in the central station or this is here. And so then he needs a couple of minutes. Is it good?
Yeah, we don't have to say it like that. That's what I'm I was considering a situation, please.
No, I would just say, I think since my next day has to go,
So I don't take it.
so everything's maybe here.
It was like considering.
Okay, then let's start with the session. We will start a little bit earlier than scheduled, but then we can also finish up earlier. Unfortunately, our chairman for the PhD session, Dimitri Papadimitriou, is not here yet. I hope he will arrive in a couple of minutes, but let's see. But we will just start, and I will take some minutes for another organizational information. So we have scheduled the groups for the quantum computer visit for Friday. So you all that want to visit can visit, and we have distributed you in 3 groups, and you can find the groups at the registration desk. There's on the wall like the 3 groups. If you have any observation or objections against the group schedule, then please let us know, and we will try to adjust the schedule. Also, a quick reminder for the Wi-Fi, because I've seen that on your Wi-Fi sheet. I think the name of the Wi-Fi is missing, so it's ITWM-guest is the correct Wi-Fi for you. There you can log in if you had any struggles with this. And the third information is for tomorrow, which is a slight change of the schedule. So tomorrow we will have only 1 hour of lunch. So we start at 12:30 noon, and so that we are able to finish up the day by 6 p.m. So you all have enough time to go to your hotel and then go to the dinner location. Yeah, that's everything from the organizational side, and then maybe let's start with the session. So. This evening session is all about the PhD students, so the next generation of quantum optimization researchers that are somewhat like the first generation of fresh, new quantum computing plus optimization research, and I think that's a great way to mix these highly interesting fields. And we start with the first talk by Romain Perrier, and maybe you can come up and the stage is yours then.
Thank you. So I'm Romain Perrier, and I'm not a PhD yet. I'm an intern, and I will present to you the subject I deal with during my internship. So it's about solving quantum chemistry optimization problems with quantum computing, and I do that with Michelin and the LPC, which is a physical laboratory at Clermont-Ferrand. So first of all, I will introduce some basis about molecular problem and chemistry. Then I will explain how to represent the problem, so a global description about quantum chemistry and quantum encoding of those problems. And then I will present a method to solve those kind of problems. And to conclude, I will conclude. So first of all, we deal with molecule, and molecules are composed by nuclei and orbitals. The orbitals are some area around the nuclei, and it corresponds to a probability distribution of the electrons. For example, there may be 2 electrons on those 2 orbitals, and we may represent an occupation of those orbitals like that. And we are interested by the energy of a molecule, and the energy of a molecule is linked to the position of each component of it. So the position of electrons and nuclei. So about orbitals, they maybe have a lot of orbitals for each nucleus. Here there are 2 for each one. And all of them are not possibly occupied by 1 electron. And here, for example, we have 2 orbitals that are occupied and 2 other that are not. And we are interested in the question, which state minimize the energy? So is it this one, or for example, this one where an electron swap from an orbital to another? And basically, to solve this problem, we may solve a problem governed by the time-independent Schrödinger equation. So we have H ket phi, which is equal to E ket phi. H is the Hamiltonian, so it's an operator that is specific to the molecule we deal with. So it's we know it when we deal with some problems. And ket phi is the wave function which is dependent on the position of nuclei and electrons. And we are looking at E, the energy, which is the eigenvalue of the problem. So the objective is to find E associated to a ket phi such that the E is minimal. So ket phi is also an unknown of our problem. And now I will explain how to create the Hamiltonian, the molecular Hamiltonian of a molecule. So I take an example with 2 nuclei and 2 electrons to illustrate the comportment of each part of the Hamiltonian. So first we suppose that the nuclei are fixed in space. And the first term of the Hamiltonian is the repulsion of each nuclei. The nuclei are fixed in space, so this repulsion will be associated to a constant. We just will have a constant here for this part of the Hamiltonian. Then there will be the repulsion of each pair of electrons. So we may express that as a double sum of a specific operator acting on 2 electrons. And then there is 2 other parts that are in the Hamiltonian, the attraction between each nuclei and 1 electron, and then there is the kinetic energy of 1 electron. And so we may express that as a specific operator that acts on only 1 electron. And we do the sum to do that for all electrons of our molecule. So how to represent the problem? So for remainder, we try to solve this eigenvalue problem. And we may express the energy as Bray phi H ket phi with H known because it is associated to a molecule that we want to solve the problem. And ket phi is unknown. And we want to minimize this expression. So why people consider quantum computing to solve this kind of problems? To understand that, I will dive in an historical evolution of the problem. So first of all, I will introduce the problem with classical methods. So first, in 1929, Slater defined the function that described the orbitals. So it described the probability distribution associated to 1 electron around the nucleus. And in fact, there may be a lot of orbitals for each nucleus. And we may sort those orbitals by energy level because each orbitals have a specific energy. And we may represent an occupation of here, for example, 2 electrons among the 4 orbitals, like that, for example. So here we have Q1, the orbital Q1 and the orbital Q3, which are occupied by 1 electrons, and the other are not. And as we see before, this thing is 1 occupation, and the wave function, we know the form of it, and the form of the wave function is the superposition of all possible electron configuration among all the orbitals. So basically, here we have 2 electrons, 4 orbitals. So we will have all the possible occupation. We will have the occupation 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and etc. And the number of parameters we have is in n choose key, where key the number of electrons, and n the number of orbitals. And so we have a combinatorial optimization problem. And in 1927, Dirac creates some operators, and we will formalize the problem using those operators. So the A3 DAG, the A DAG is the creation operator. So for example, here, A3 DAG will create an electron in the 3rd orbitals. And there is then the annihilation operator, which is A3 here. A3 will delete an electron if there is one on the orbital 3. And so we may express the wave function using those kind of operators, which are called fermionic operators. And all those operators act on a specific state, which is the void state, where there is no possible, no electron in the orbitals. So we may also express the Hamiltonian using those kind of operators, because in fact, acting on one electron is like destroying it somewhere and recreate it in another place. So H1 will become AP DAG and AQ, so we will destroy the electron in some orbitals, and we will recreate it in another orbitals. And we may do the same thing with 2 electrons, with this time 4 specific operators, 2 creation and 2 destruction. Then the first method to solve the problem arises in 1935 with the Hartree-Fock method. In fact, here we want to solve the exact same problem as before, so find the wave function with this form. However, there is a particularity. Each parameter are located, we look at each parameter in n. So basically, all the operator will be equal to 0, so, except 1, which will be equal to 1. And we are looking here at only one occupation. There is no superposition, and we are looking only at one state, in fact. And we may plot the associated energy. So here, in this plot, each dot represents an execution of the Hartree-Fock method with distinct Hamiltonian for the same molecule. In fact, the only thing that changed is the constant term in the Hamiltonian, so the distance between the nuclei of the molecule. And then there was the optimal method in 1952, the full CI one, which is optimal because we are looking this time with all the coefficients in R. And so we have the superposition of each state. And to solve this problem, we need to minimize a specific function depending on H. And H is a matrix of size n choose key times n choose key, with n the number of orbitals and key the number of electrons. So we may do that for H2 and we find a better energy. However, we have a problem because if we want to solve this for 100 orbitals, for example, we will need 10⁴ bytes in storage. And if we want to solve the problem for CH4, for example, we need to use all the memory of Fugaku if we want to solve exactly the problem. And if we want to deal with a really interesting problem, like, for example, the isoprene, well, we can't do that with the optimal method. And so when quantum computing arose in 1985 with the Dutch algorithm, some people try to encode the problem with quantum computing, to find a quantum encoding, in fact. And to do that, they read a lot of paper, and they find a paper written in 1928, which talk about the Jordan-Wigner transform. And we may use that to map spin operator to fermionic operator and fermionic operator to spin operator. And so, as we have seen before, the Dirac's operator encode an occupancy. So here, A1 DAG, A3 will correspond to the occupancy of key 1 and key 3. And we may use the Jordan-Wigner operator to encode the same thing, except this time we may express that in qubits. And the encoding is quite simple. In fact, we have the same number of qubits as the number of orbitals. And if one orbital is occupied, we'll set the associated qubit to 1. And if not, well, the associated qubit will stay at 0. And we may so express a specific state with a circuit, a quantum circuit. The creation operator on the kth qubit is written like that. So it's a product of Pauli gate, where Zi is the application of the Z gate at the IF qubits. And so the creation operator is the product of the ZA, and we have then xk minus a yk, and we divide that by 2. I will do a brief example with k equal 1. So we only have x minus a y divided by 2. We may express that with some matrices. We may do the calculation, and we find this matrix, so 0, 0, 1, 0. And if we apply the state k0, so one orbital is not occupied, well, we will occupy it because the state will go to 0 to 1. And if we do that for a state that is already occupied, well, we will go out of the computational basis, and so it's not interesting. And we may define the annihilation operator in the same way. This time we don't add x and y. We don't subtract, x and y. We will only add them. And so we may encode the wave function not with the Dirac operator, but with Jordan-Wigner operator. And we may do the same thing for the Hamiltonian. And we may encode the Hamiltonian with Jordan-Wigner operators. And because we use Jordan-Wigner operators, we may express that as a sum of tensor product of Pauli gates. And we may then do something with the Hamiltonian. I will explain that later. And in 2013, the development of variational quantum eigensolver arose. And some people now, and since then, try to solve quantum chemistry problems using this kind of algorithm. And so I will present briefly the VQE method, so variational quantum eigensolver. It's an hybrid method. There is a quantum part and a classical part. The quantum part is a quantum circuit, and I will present each step of it. So the first step is the initialization of the circuit, and we may initialize the circuit to a specific given state. And as we have seen on the slide, we know already a good state that may be a solution of our problem, and this state is the Hartree-Fock state. So we may simply put the initialization at the Hartree-Fock state. And then we apply an ansatz, which try to explore the Hilbert space. And the objective of it is to try to guess the form of the wave function. So try to find the occupation of the orbitals. Here, an example of a naive ansatz. There is no motivation, and so we will try to explore all the space. But it exists other ansatzes where we construct them with excitation operator, and in fact, there is a kind of motivation about chemistry problem behind, and we will try to explore a smaller part of the Hilbert space. Then there is the projection and the measure. Why a projection? Because in fact, here we don't want to measure qubits, we want to measure an Hamiltonian. And we have expressed our Hamiltonian with tensor product of Pauli gate. And in fact, to measure it, we will try to estimate it. So we will run the circuit, the ansatz, for each part of the Hamiltonian. And then we want to measure it in a specific basis. We want to do a Z measurement. And so when we are in X or Y, we need to do a projection onto the computational Z basis to do the right measurement. And then we measure the result. And we go on the classical calculation part, where we do the energy computation. So we sum all the value we got for our measurement. And then we will do the optimization step. So we will change the ansatz parameter, and we will try to re-execute the circuit and try to converge to the lowest value. So what I have done during my internship is quite specific. I implement the VQE on a supraconducting quantum computer, so with a supraconducting paradigm. And I also do that for a photonic paradigm. What changed is, in fact, the photonic encoding is higher. We work in an higher space than qubits encoding. And what I have done is I've done a qubits logic encoding and a qudits logic encoding. And the result I've got, I compared the naive ansatz and the chemistry motivated one on the depth of the ansatzes. And you can see that there is also two different plots for the UCCSD, so the ansatz that is motivated, because there is also the adept VQE. Here, the adept VQE, we construct the ansatz at each step of the algorithm. We will add something in the ansatz, in the circuit. So we don't execute the same circuit at each iteration of the algorithm. I also compare on the number of evaluation of the cost function, and we do a lower evaluation with the chemically motivated ansatz. And of course, I compare the different ansatzes with the accuracy. And we can see that if we use an ansatz that is motivated, we will have a right accuracy, because in fact, quantum chemistry problems are quite specific because we want to have an accuracy that is minimum. And here's the black bar. And we see that when we use an ansatz that is not motivated, we don't reach the right accuracy. And here the accuracy is calculated by a subtraction of the optimal method, so full CI1 and the VQE. And I do that for 3 molecules, so H2, LEH, and BEH2. And I compare the two paradigms, and globally the curve is quite the same, but not exactly. And about the ansatzes, in green and red, we have the photonic ansatzes. In orange, the supraconducting ansatzes. The 3 of them are not motivated with chemistry. And in blue, we have the ansatz that is motivated with chemistry. And we can see that the depth is higher with the ansatz that is motivated. However, the number of parameters is lower. So it may be interesting to try to use this kind of ansatz. So, to conclude, we may be aware that there is some distinction between some encoding. So if we use supraconducting or photonic encoding, we will not deal with the problem in the same way. And for chemistry problems, the ansatz are really important in the VQE, and we may think well of what kind of ansatz we use. And in my opinion, it's also an unfair comparison between the optimal full CI method, which has decades of optimization and amelioration and improvement, and an emerging method like VQE, for example. And we saw this morning with Pierre Jäger that perhaps the SQD may be a better option to solve this kind of problem. And thank you for your attention. Two last things to say before end the presentation. First one, I'm looking for a PhD in quantum computing. And second one, if you're interested in quantum chemistry, I was a computer scientist. I am a computer scientist. And I recommend you to read the book of Szabo and Osland, Modern Quantum Chemistry. It helped me a lot to understand the problem of quantum chemistry and deal with my subject during this internship. So thank you. And if you have a question, you're welcome.
So, you're free to shoot questions.
How do you choose the answers from the chemistry problem?
I choose it by reading literature. There is a lot of kind of ansatz, a lot of ansatz that is motivated by chemistry, and I choose this one, so UCCSD, because it, for my problem, for H2, LEH, and BH2, I find the better result. I try a lot of ansatzes, and I show them because it's a better result.
You can try 10 things in literature, one of them looks better, is it like physical quality of the data?
There is physical quality in each ansatz. For example, here you see CSD, we initialize the ansatz to a specific state, generally the R3-4 one, and we will construct the ansatz by adding excitation operator. So we will try to pass one electron for example, the key 1 orbitals to key 3 or key 5. And we construct on that like that. We try to put in superposition specific excitation of the initial state.